Hi guys, welcome back. It's time for some more data structures. Let's review for a second. We've dealt with linked lists and we've talked a little bit about trees. We had an in-class exercise on trees. We also did project 3, which was all about linked lists and adding elements to linked lists in different order depending on some parameter. In class we've discussed ring buffers and queues and we've implemented some of those guys. But what's coming up next is project 4, which is a combination of linked lists and binary trees. What we're going to be doing is parsing an input string through a web service and then converting that input string into a tree representation of an algebraic expression and also a string representation of an algebraic expression. And finally, we're going to be looking at debugging projects in Cloud 9, a little bit more complicated projects like project 4, for example. So let's get started on that. We want to look at project 4, which is an application of parsing and converting reverse Polish notation into algebraic notation. So the idea is you get an expression that's in reverse Polish. Now if you're not familiar with reverse Polish, it's pretty simple. You just read from left to right, and every time you encounter a value, you imagine pushing it onto a stack. And every time you encounter an operator, you imagine the operator operates on the top value or the top two values of the stack, depending on the kind of operator it is. So if it's an operator that requires two numbers, it operates on the top two. If it's one that only requires one number, then it only operates on the top one. So for example, plus is an addition operator. It takes two numbers to add. So plus takes two. On the other hand, negation only takes one, plus minus. We're not going to implement that operator in this class, but or x squared only takes one argument, log of x only takes one argument, and we're not doing any of those either. So the only operators we're going to implement are addition, subtraction, multiplication, and division. So let's see how that's going to work.
Hi guys, welcome back. Here I am in Cloud 9. I'm going to go ahead and clone the repository, and because I've already solved the problem in my repository, I'm going to go ahead and copy the original implementation back into my source tree. So this should be pretty much what it looks like when you guys download it. And if you type make, it will go ahead and build. But if you run the resulting executable, none of the tests will pass. And that's because if you open the implementation file, you'll see that in fact the implementations are all empty. They're just minimum implementations to satisfy the interface. So any pointers are returned null, any what else? Get operator returns a -1, which is just failure, and so on. So your job is to go through and implement all these functions. So actually, let's talk about these functions. The idea, of course, is that you're going to implement a linked list of trees. The idea is you're parsing these RPN expressions. When you encounter a number or a token that's not an operator, so it could be a variable name or it could be a literal number, you'll put that into an empty tree with only a root and no leaves and push that on the stack. Whenever you encounter an operator, you're going to pop the first two things on the stack off, add those as leaves to the operator, the left and right operand of the operator, and then push the resulting tree back on the stack. Now the trees that are on the stack could be simple nodes with no leaves, just a root, or they could be complex trees with many subtrees and sub branches and so on. Doesn't really matter. The point is you're going to pop the two things off, apply the operator, push it back on. If the RPN expression is balanced, in other words, if there's enough operators to consume all the values, then you should have a single tree left on the stack, which is the translation of the RPN expression. So list length is the length of the linked list that implements the stack. So really, I guess it should be stack length, but it's a linked list, so it's called list length. List print is a utility I'm providing for you for free that will help you in debugging if you want to print the contents of the linked list. And notice that it allocates a buffer. It prints out the address of the head of the linked list, and then what it does is it clears out the buffer, calls tree sprintf. This accepts the root node of the tree and a buffer into which to print the string representation, and then it prints out the buffer and frees it. So it allocates a buffer, prints into the buffer, and then frees the buffer. Then it calls itself list print on the next node in the list. So this will go through and print out everything in the linked list. So if you run into some bugs and want to figure out what's going on, this might be helpful. So list node free just frees a single node from the linked list. List free frees the entire linked list. List node new allocates a new node, so this should do whatever is necessary to allocate a new node for the linked list. List push head, you give it the current head, you give it a tree you want to push, and it should push that tree onto the linked list. List pop head, you give it a pointer to a link node pointer, because it's going to modify that guy, and it will return the tree node pointer that used to be on the top of the stack. So this pops the first tree off the stack and adjusts the head to point to the new top of stack. Get operator takes a pointer to an array of valid operators, and it returns the index in that list. So if the valid operator is the first on the list, it would be a 0, 1, 2, or 3 in this case, since there are 4 valid operators. Although if you want to invent more operators, you're certainly welcome to. Tree node new creates a new tree node. Tree node free frees the memory from a tree node. Tree size counts the total number of nodes in the tree. Tree free frees the entire tree, all the tree nodes in the tree. Tree add node basically takes this is a really simple function. It sounds complicated, but basically you give it the root of a tree and the left and right values for the node pointer, and it just assigns those. So it's just a shorthand way of assigning the left and right pointers to a tree node. Tree sprintf is going to recursively descend into the tree and print out an algebraic notation expression that represents the tree. And we'll see this. This is used to produce the output on the website that gives the algebraic notation, so you can play with that. Tree visit descends the entire tree, starting at the root, and for every object in the tree, it calls visit func. Visit func is just a callback function. It accepts 4 arguments: the value of the node, a pointer to the node itself, a pointer to the parent of the node, whatever the parent is, and then a pointer to a void, which is used by Python to wire it back up to the Python object so it can call back a Python function. So it's basically a pointer to a Python function, but you can just think of it as a void star. You just need to pass whatever you get here as a void star, you need to call with that same void star. Tree printf is another utility to help print the tree. So it allocates a buffer. Allocates a buffer, not with malloc, just on the stack. It copies an empty string into the buffer to clear it out, and then it calls tree sprintf to print the representation of the tree into the buffer, and then it prints that with a new line. So this just basically prints out the guy. Parse RPN, this is the most important function of all. It takes a string, an RPN notation. It takes a list of valid operators, and then it parses the RPN expression and converts it to a tree, an algebraic tree. And the way you do it just as I described, you go through the string. For every token, you decide if it's an operator or not. If it's not an operator, you push it on the stack. If it is an operator, you pop the 2 elements off the stack, top 2 elements off the stack, and combine them with the operator to make a new tree and push that tree back on the stack. So that's it. That's all the code. All right. So let's close that guy up. Let me, I'm going to go ahead and, just for grins, copy back the correct implementation just to show you how it behaves. And that way, so you can make the Python extension, then you can make PyInstall, which installs the Python extension into your Python library, so that means you can load it from anywhere. So now if I build a.out, it says all tests pass. I can say make test, and it says all tests pass, and all memory was freed, everything's dandy. So I've got my implementation is in there. If I say Python 3 and then psource parse it. So parse it is a Python function which accepts an RPN string. So let's say 3, 4 plus. That's an RPN string that should add 3 and 4. And notice it does two things. It produces a bunch of notation here. This is called a GraphViz program, a GraphViz description of a diagram. That's a diagram of the binary tree. And then it also has the algebraic notation here, 3 plus 4. So that is RPN for 3 plus 4. Let's go ahead and copy that that digraph, and then I'm going to go to planttext.com, and I'm just going to paste this. PlantText is a cool site that lets you create diagrams with text. So I'm going to just take that digraph and paste it in here, and we'll see what it looks like. Notice there, it's a tree. It's got a plus operator with a left and a right, and it's got two nodes which are 3 and 4. So our program actually produces, it actually produces a diagram in GraphViz notation of the tree, so you can actually watch it. Let's see if I add a 5, 6 plus times. So what that means is it's going to be 3 plus 4 and then 5 plus 6. So if I type this in, I'll have two trees on the stack, a 3 plus 4 tree and a 5 plus 6 tree. And if I put the star operator, it's going to pop this tree off, and multiply the two trees together. So let's see what that looks like. Algebraically, it's 3 plus 4 times 5 plus 6. Let's go ahead and grab the digraph, and let's paste that into the page here at PlantText and see what that looks like. And you can see that's exactly what we got. 3 plus 4, 5 plus 6, and then star. So I'm multiplying 3 plus 4 times 5 plus 6. There you go. Now the really fun thing, if you think of it as fun, I think of it as fun, I think it's pretty kind of cool, is that there is cooked up now, if I say Python 3 Flask App, this actually runs a web server which we can now visit. So let's do it. I've got a, I know. Okay. I need to go back to Amazon, and let's look up the details of my running instance. So I'm going to go to my running EC2 instance that's running the Cloud9, and I want to grab this IP address here. So I'm going to grab that guy, and I want to look at the launch wizard that I'm using to control the security of this server, and I want to look at the inbound rules. Now I've already edited my inbound rules. I'm going to close this out, EC2. Okay, so I've gone to my EC2. I want to go to running instances. I want to check this IP address, copy that guy to the clipboard. Then I want to check my security groups for this guy, and I want to look at the inbound rules. Notice I've got port 5000 is allowed from anywhere. If you need to change that, you can click Edit and add a new rule. The key is to let port 5000 come from anywhere. You could set it to your IP address as well if you want to be a little bit more secure. But the point is, I can now come back here and paste that IP address in, and then say port 5000, and you'll see that it's running my little Flask app. If I go back, notice it got a hit from that location. So I'm going to type A, B, plus, and oh, it's still going. There it goes. So there's my tree, AB plus. So if I say CD plus, now notice it changed to CD plus, but that's because this plus doesn't consume both the trees. So if I say star here, now I've got a star, I've got AB plus, CD plus, star. If I wanted to divide them, I could just say divide, and notice the algebraic notation shows me here what this is what your tree sprintf is going to do to sprintf the buffer to hold the algebraic notation. But it's cool that the diagram actually shows I could say G plus, and that adds another tree there. Notice the other way you could do this is to push all the values on the stack, and then let's see, if I said plus, 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 that would add A, B, and C. First it adds C and D, then it adds B to that, that's what this one's doing, then it adds A to that, and then we could say G divide. And now that's actually equivalent to what we had before, I think, but anyway, you can see there's different ways to spell with RPN the same, you get the same arithmetic result, but there's different ways to order the operations so they happen in a different order. Alright, so very exciting. Let's pop back. We'll go ahead and clear that guy out, and that's basically how that works. So you have to write all the functions. You want to type make to build the C. Let's just go over that again. We'll type make clean to clean everything out. Make builds the C executable and all the objects. Make py builds the Python extension. Make py install installs the Python extension, so it's in your Python library that you can get to from anywhere. Then you can run parse it to test that the thing actually works, and then when that's working, you can run the Flask app by saying Python Flask app, and it actually goes, and then you can use it. So I hope that helps, and we'll talk to you guys soon. So I want to take a second to describe the Flask app. It's basically a very simple web framework written in Python. And I'm not expecting you guys to learn how to write Python code, but I wanted to describe how it's wired up to your application so you can see why it's important for your application to handle errors in certain ways and things like that. So first of all, when you hit the web page, your port 5000, you're coming to this route. It's the default route of the web server. So the web server is going to call this method called home. It's going to check and see if the method is a post, which means you hit the submit button. If you click that submit button on the web page, it's going to do what's called a post, and the form, the text you type into the form is going to appear in an object called the request.form object with a label RPN. Then Python's going to strip any extra space from the front and back of that string, and it's going to split it into tokens, so it'll produce a list of tokens. Then what's going to happen is we're going to join those tokens with a single space. So if you put extra spaces in your string, this Python should basically strip those out, is what's going to happen. And so the RPN will be a single space delimited list of strings. All right, it's a string with space that has a single space between tokens, is what it boils down to. We're going to set the error return and the result return default to none, And graph in algebra, graph is going to be the digraph, the string that represents the digraph, and algebra will be the algebraic notation. If it got some RPN, it's going to go through the RPN and check to make sure it's only got allowed characters. Allowed characters are digits, the lowercase ASCII characters, and the uppercase ASCII characters, and then the 4 operators, plus, minus, star, divide. Okay. It looks like it's also allowing space. Okay, so there you go. Then what happens is, assuming that the characters are all okay, if it's still everything's still okay, then it runs a subprocess. It calls Python 3. It runs parse it with the RPN that you specified, and then there's an extra argument to tell it to escape the new lines for JavaScript, which we'll see how that works. Or at least you can try it and see what it, if you add another argument, it escapes the new lines. And then notice it's standard out and standard error are both being set up as pipes. So basically this allows us to read from standard output. That'll give us the diagram. Or if there's an error, it'll look in standard error. And this is why it's so important that if your program has to crash, that it should put a useful error message out on standard error. And that way the web server can read from standard error and try to display a useful message to the user. So result is the return code. Well, result is the result object from the subprocess run. If result comes back non-null and the return code is 0, that means the process terminated normally. And that means we probably got an answer. So we'll go ahead and this is some string manipulation to go and separate out the graph text from the algebra text. Here we are trying to strip off the last escaped new line because it looks ugly on the screen. And if everything's okay, then we're going to pass the graph and the algebra onto the template. We'll set the error to null, to empty string. On the other hand, if the return code is not 0, that means there was something bad that happened. And here's where we look at standard error and try to figure out if we can display a useful error message on the screen. Anyway, all the results, the RPN that you typed, the graph that we got back from parse it, any error messages that we found, and the algebraic expression we got back from parse it, all get sent to the display template. And I'll go ahead and pull up the display template. It's here, just so you can see how that works. So this is basically an HTML document, but it's an HTML document that has extra information. Here's the form that with a field called RPN that you can type RPN into. If there was an error, it displays the error. If there's any algebraic notation, it displays the algebraic notation. And if there was a graph, it pulls in some JavaScript code and renders the graph using JavaScript. And I'm not going to get into that. If you're interested, you can look at it. But that's the whole template. In fact, that's the whole application. So we just went through it. If you have any questions about this, you don't have to write anything for this project, but I just wanted you to be aware basically how that worked.
Okay, so the idea is we're going to use a stack. We'll actually implement a stack as a linked list to process the reverse Polish notation. What we'll be doing actually is building tree data structures and pushing them onto the stack in order to represent these generic expressions. So let's see how that works. So we start with an empty stack. The head points to nil. We come along to the first token and we create an elementary tree with no leaves. It just has the value 3. And we push that guy on the stack. Then we come to the value 4. We push that guy onto the stack. Then we encounter the operator plus. What do? Well, we pop the 3 and the 4 off the stack. We assign pointers to 3 and 4 to the left and right sub-pointers, the left and right members of the record structure, and we set the value to plus, and then we push that whole tree back onto the stack. Remember, the stack is a stack of pointers to trees, so or tree nodes, technically. And so a tree node could have sub-elements, the left and right pointers that point to other things. So that's now a tree that's pushed onto the stack. Then we encounter a 5, right? So we push a 5 on the stack, then we push a 6 on the stack, then we push the second plus operator on the stack, and by the time that all happens, we've got a situation like this. So we've pushed the 3 and the 4 on the stack, we've pushed the 5 and the 6 on the stack, along with their associated plus operators, and then we encounter the operator star, which is multiplication. So that means we're going to pop the 3-4 tree and the 5-6 tree off the stack and use those as the arguments to the star operator, the operands, and then we push that back on the stack. So when the thing is done, we have a single tree on the stack, and that's a tree that represents the entire expression. Then we can convert that into a web page, convert that into an algebraic expression, and so on. So in class this week, we're going to work on how do you actually parse tokens, how to use strsep, and how do you run those web services. I will also talk about that in the video here, so you can see how that goes. So let's look at strsep and see how that operates in a little demo.
Okay, one of the last things we're going to do today is to talk about parsing strings into tokens. And the function I'm going to suggest to use for this is called strsep. I do want to point out that I'm using a runner. I went ahead and cooked up a runner that took out the C standard 99 so that strdup and strsep don't raise warnings. So you're welcome to do that, or if you don't mind the warnings, I guess you can live with them. Or you can put prototypes in for strdoup and strsep. So let's go ahead and begin. The idea here is I define an input string, which is a string with some spaces in it. I'm going to call this parse function, which we're going to write. So the first thing we want to do is to make a copy of the input, because strsep actually destroys a string. It inserts null characters into the middle of the string, which tears it to pieces, and so generally you don't want to do that. A function doesn't normally want to do that to an input string. The caller does not expect you to destroy their string. So we're going to make a copy. I'll use strdoup for that. Remember that allocates memory and copies the string contents into it. Now the other thing we want to do is we want to be able to free that, and if I don't make a copy of the copy, I'm not going to make a copy of the string, I'm just going to make a copy of the pointer. So the original copy is just a pointer that we can free later, because when you use strdoup, it's going to actually monkey with cpy, and I want to, let's just call this, let's give it a real name, old copy, call this copy. Okay, there we go. And then I also need a token, so the token is just going to be a pointer to the immediate token that I find in the string, and I can just don't need to initialize that. Okay. So I've got a token, I've got a copy of the input, and I've got an original copy of the input. It's just a pointer that I'm going to free later. So let's begin. So I'm going to say while token is strsep of a pointer to the copy, like that. And then I'm going to put a list of characters that can act as delimiters. In this case, it's just spaces. Okay. And then I want to say while token returns anything other than null, I want to keep going. And all I want to do is say printf, we found a token, %s, like that. And then when the loop is finished, I'd like to free. Let's free the old copy. Copy. Because I don't want to free copy because copy has been changed by strsep. Notice I'm passing a pointer into strsep, which is constantly updating the pointer copy to point to the next token in the string, and it's inserting null characters into the character buffer. So let's see how this works. So if I run that guy, it says I've got a problem, cannot set any breakpoints. Let's see, car star argument, you found a token. What is the actual problem? Oh, I forgot to put the token in there. There we go, boom. And let's set a breakpoint here. So I'll go ahead and say stop and run again. And we got a breakpoint. Okay, so let's delete this thing. Remove watch expression. Okay, so we'll step. So now the input is this is a string with spaces. The copy is this is a string with spaces, and the original copy is this is a string with spaces. Notice that original copy is a pointer to the original address of the copy, and it's different from the input. So it's going to say while token equals strsep. Now look what happened. Token is now pointing to 602.010. The original copy still points to 602.010, but copy now points to a later pointer. It's pointing to is. So it's moved. strsep has modified copy to point to the beginning of the next token, whereas the original copy still points to the original first token, and the space has been changed to a null. So that means this is now a separate string in its own right, and then we're going to print out this, and then we're going to keep going. Notice it happened again. Token now points to is. Is now terminated with a null character, so strsep has modified that string and put a null character in there. Copy still pointing back to this. So that's the original pointer returned by strdup. Copy is now getting modified each time. It now points to A, so it's gone on to the, it's now pointing to this A. Token points to is. So copy and token are marching down the string. Let's go ahead and let the thing finish. So it went ahead and printed out this is a string with spaces. We freed the original copy because that was the thing that was returned by strdup, but we let strsep monkey with the copy and adjust the value of the copy pointer as it went through. Probably a little confusing. Take this example, we'll play with it in class, and we'll see you next time.
One other thing, when you're not just running a program from the command line and either it crashes or it doesn't, when you're running a web service, you need to be able to identify when the program has crashed. You know there are numerous error conditions in the code where we print an error and then exit the program because we don't have any sane way to sort of deal with it. Like if you run out of memory or you pop too many things from the stack and you just need to say, I give up, this is not going to get me anywhere. In order to make that work in a web environment, it's nice to have a distinct way of indicating there was an error and to send some kind of helpful error message back to the web process so it can display that for the user. So the way we're going to do that in this project is to send the error messages to stderr and also to exit the process with an indicator that there has been an error. So the way you'll do that is to use fprintf to print to the stderr file. Stderr is a standard file in C. Like standardout is the standard output file, stderr is the standard error file. And also, we're going to exit the process with a number other than 0. Remember, main is a function that returns with an integer. If everything goes well, it returns with a 0. But if you call exit, it'll return with whatever value you supply to the exit function, which we usually make -1 or -2 or something like that. You can actually use different numbers to indicate different error conditions if you like. So what we're going to do is send an error by exiting and using fprintf to send a message to stderr. So let's see how that works. Basically, here's an example from the implementation file that you get in your repository. This is one of the few functions that I write for you, and I just want to point out that if the big buffer, if bbuff doesn't get allocated, if it ends up being null, then it drops down into the else clause of the if. It prints an error message to stderr. No bbuff memory. Probably what it should also do, although I didn't actually do it in this case, you could also say exit -1. If you have this is not as dramatic an error, basically just fails to print, which is, there's no world-shattering consequence of not printing, I guess, but it does at least send an error. But what I would say is if you have an earth-shattering error, you might call exit -1, and that would terminate the process and give a decent error message. So there you go. Finally, we want to talk a little bit about debugging projects in Cloud 9, and so let's see how that works.
Okay, I wanted to quickly show you how you can debug this program for Project 4 in Cloud 9, because I think we're reaching the level of complexity where debugging in the IDE is probably useful. The thing is, if you just try and run, if you click the Run button in the IDE in our main program, main.c for the project, you'll see it can't find all tests, because all tests is defined in the test RPN converter file, and of course test RPN converter calls functions defined in implementation.c. So the simple setup that's available in Cloud 9 by default is not sufficient to handle this complicated situation with 3 source files, all that need to be bound together into a single executable. So the thing is, if you click over here, you'll see that there are these runners to run different kinds of things. It turns out you can, if you edit the runner and save it as a new file, I've edited it, and actually, let's look at the default runner. If I look at runner and say edit runner, you'll see this is the runner that's built in to handle C. And it has 2 situations. One, if debug is set to true, then it does this stuff, otherwise it does this stuff. And you'll notice that in this section, it's setting some extra flags to handle debugging. And file is the name of the file you're editing. So what we need to do is to add more lines to this runner to compile implementation.c, main.c, and the test program, and then link them all together into an executable and then run it. So actually that's what I've done here. If you go back and look at my runner, or my C, and then you say edit runner, you can see the slightly more complicated version, and I would recommend you can just steal this and use it. Actually, I should probably I'll post this to Ace so you guys can use it. But basically it compiles the main program, compiles the test program, it compiles your implementation, and then it links them all together into a single executable, changes its permissions to make sure it is executable, and then runs it. And then it does the same thing in the case of no debug, except there's no debug flag here, and then it runs it just by running it, not by running it through this other JavaScript monkey business. Anyway, I will post this to Ace, this runner, and then you can just install it in your runners directory. It goes in, let's see if I make a new terminal window. If you look in Workspace, there's a C9 directory, ls-la C9 runners, and you can just copy the file there. In fact, I can let's get rid of the my C run squiggle. We don't need that. Boom. Okay, that's all there is to it. I'll post that and notify you guys. And then anyway, let's go ahead and see how that works. So if I run this guy, you'll notice it says new custom running. So it tells me that I've got the custom runner, and it says all tests pass. If I turn on debugging, and then I can set a breakpoint here. Now if I switch to debug and run the thing, you'll see it actually hits the debug breakpoint, and now I can go in and actually pop through the tests. If you want to look and see what happens in a test, you can step through it and actually get into your code and step through it and see what's going on. So hopefully that will be helpful. We'll talk to you guys soon.
All right, that's it. So we'll talk to you guys next time.